This car has been fighting me tooth and gear. I quickly discovered the 150 amp breaker I selected for the front part of the alternator circuit was undersized for my application. Circuit breakers are thermal devices, and an engine bay is probably the worst possible place to install one. Once my engine's hot, it trips, and it can't be reset without waiting for everything in the engine bay to cool off. I spoke with a robotics technician about this problem, and he stated that these particular devices only operate continuously at 60 to 70% of their peak rating. Well, I have a 105 amp alternator now, and that means that a low battery condition where the alternator is charging will exceed that load. Add heat and things only get worse. I had to replace my 150 amp breaker with a unit twice its rating so that it can withstand the ambient heat as well as a continuous 105 amp load. Then I go boost leak test my intake system and discover the old junkyard single core Sonata radiator is leaking. I absolutely have to replace it or else I'll be overheating everywhere, but I might as well go ahead and test for boost leaks while I'm here. Looking under the car and making sure you have no bolts left over is just the tip of the iceberg after you finish re-engineering whatever your garage experiment is. You don't really get the full diagnosis of the health of your build until you go out, pound on it, and then pressure test everything. I found lots of boost leaks on this untested equipment, and the way you deal with those is to solve the worst ones first and then go on down the line finding the next one and the next one until you've squashed all your bugs. This J-pipe is a used part that's new to this build, or I should say that it's returned for another shot at greatness, but it's got some problems. The clock angle isn't perfect on this turbo, and it's got several pinhole leaks in its welds that need attention. Well, I have access to a friend with a TIG welder who can fix this little problem for me, but before I enlist his help, it's only polite of me to clean up and prepare the part for welding so that he doesn't have to. After all, he's the one doing me a favor. My bench grinder wheel is already toast, so I don't even feel bad about abusing it like this. The wire wheel makes short work of the paint, and pretty soon we have a part that can be welded back together without much along the line of burnt toxic paint vapors or globs of slag in the way. A TIG welder's nice because you can melt together what's already there, and you can also add filler rod as needed. But with TIG welding, preparation is everything. In order for this to turn out well, I'm removing as much of the old welds as I can so that a more uniform weld can be achieved. Jamie left lots of material for us here that we can puddle back together when he made this, and I can't fault him for any of it. He did really well with a flux core welder. There's just not a whole lot of room here to play with around these two bolt holes, or bolt hooks I should say. They're really not holes. They're cut like this so that the J-pipe can be clocked, but when clocked properly, the bottom flange leaks. I'm going to do whatever it takes to stop these leaks because that's what I have to do, or else I'm wasting my time tuning airflow and fuel tables. Given the fact that this car is a hodgepodge of factory parts and custom fabricated stuff, wherever those two kinds of parts meet are where I'm most likely to find all my problems. It's also without any regrets, but with some embarrassment, that I'll own some of my mistakes in this video. I gave some of these parts too much credit. Fortunately, one of the mistakes I made is working out to my benefit because of what's in my spares pile. So this is the big bug squashing episode. Bug number 1, RTV is not an appropriate band-aid for a leaky metal compressor housing gasket. I knew better and I did it anyway. We'll get to why it didn't work in a minute. I just need to clean up the flange so that I can show you, but we've got to get this pipe welded back together before I do any of that. So here we are at Chad's workshop. Though I haven't managed to convince him to start his own YouTube channel yet, so far he's contributed lots of tools, knowledge, and labor to help my channel succeed. He even cuts my grass so I can keep editing videos instead of doing yard work. Hell of a guy. He's got this fancy Miller Diversion 180 and the skills necessary to weld up and seal the junk scrap I bring him on a regular basis. Steel, aluminum, doesn't matter. This stuff takes time, it takes skill, and it takes shop supplies that often need to be replenished. I could have done this particular part with my MIG welder at home, but not with any degree of control and precision that comes with using a TIG welder. So Chad wins. I'm very grateful for his help and support. Some of the fixes in this video would have been impossible without him. Well, that's it for this bottle. Dang. I guess I'll get to refill this because at no point do I ever want my mechanical problems to become someone else's expense. Here's the J-pipe after Chad ever so kindly even painted it for me. All that prep work and welding turned out so nicely. It is possible to use RTV to seal an intake pipe with. It can't penetrate deeply enough into metal to hold on to it, but it can if you give the RTV something else to hold on to. You can use a paper gasket to solve this problem because it's porous. Use a thin even coat of gray RTV on both sides of it, bolt it all together firmly and let it set. After it dries, it isn't going anywhere, and the paper helps the RTV stay put. This is always the kind of gasket that fixes my boost leak problems with this particular type of compressor flange. But now that it's all sealed up, I still can't even hold more than 3 psi. I've got another major leak somewhere else, and it looks like I've got a problem with the blow-off valve. It doesn't appear to be just the gasket between the blow-off valve and the flange, it appears to be the actual flange itself. Yep, the bob flange appears to be glued to the pipe, and there's an inch-long crack in each side of the glue. Glued. This undoubtedly worked great when the glue was fresh. It could even be glued back together for a temporary fix, but you know me. I'm going to get Chad to glue it back together with aluminum. After cleaning up the flange and cleaning out all the glue with wire brushes, X-Acto knives, emery cloth, and finally a Scotch-Brite pad, it's back over to Chad's to see if this old part can be salvaged so that I don't have to fabricate anything from scratch. I gifted him with the arduous task of welding a 1/4-inch piece of flat stock to the thinnest schedule aluminum tubing that can be found on eBay. This is an extremely difficult task because of how easy it is to blow through this kind of tubing. I told him it doesn't need to be pretty, it just needs to seal. This kind of fix that once accomplished, I won't have to keep coming back to later to fix again and again. The two screws on the flange are steel and they presented me with other challenges which we'll get to in just a minute. After welding was complete, I flat filed the flange and made another paper gasket for it. I'm all out of factory gaskets, so this will have to do. This is really just more of the same, but if you want to make your own gasket for a factory blow-off valve, you have to leave at least one side teardropped so that it can line up with a hole in the bottom of the bob that helps it work properly. That needs to have access to the pressurized portion of the flange. Don't fail to cut that part out or use too much RTV so that it squishes in there and blocks it. Thin coat on both sides, honk it down, and then boost leak test it. Well, it looks like a valiant effort, but it still needs work. It appears that not only the welds, but my flat filing job also isn't quite cutting it. This paper gasket RTV trick only works if both flanges are completely flat, but clearly this part is doing much better now. 16, 18, and blowing the boost leak tester off the compressor inlet at 20 psi. To have pulled that off is a major improvement. I'm going to put this thing back together and drive it into the garage. Since the radiator needs replacement, I went ahead and drained the coolant so that I could go ahead and... Oh, for crying out loud! Really? Really? Those two things are supposed to be in different containers. You're never supposed to see that. That's bad. Coolant is like 15 bucks a gallon now, and it's a shame to see such a new pristine gallon of green stuff go to waste. Well, there's a reason mechanics use these red oil cloths. They're called oil cloths because they're terrible at cleaning up water-based chemicals. Watch. If you end up with oil and coolant in the same pan, you can simply put a clean oil rag down on the surface of the coolant and then remove the rag, and all the oil goes with it. Get another one and go around the edges. Just make sure you got it all, blot the rest up, and then you can pour out and reuse the coolant. But why do I have oil in my coolant? Normally that's an unfortunate event caused by a head gasket failure, but looking around I see a leaking oil cooler. I don't know the health of this part because I bought it in a well-used and broken down car that I stripped and crushed once upon a time. I thought the oil cooler might have been squished and leaking, or I did something wrong with the thread sealant on the oil filter center post, but...
Oh my goodness. That's all it is. That's all it is. That's all it is.
But it appears that the heat cycling and the quick short drives that I took it on were enough to vibrate it loose. I've read horror stories about this, but it's never happened to me before. I caught it just 1/8 of a turn before I became a part of that statistic. I'll need to keep an eye on this now that I know that this oil filter housing is capable of doing that. Oh well, disaster averted, and I've got to change the break-in oil anyway. At least I managed to save the coolant. Maybe you got to learn something about oil rags in the process, maybe not. But on with the oil change. How boring is an oil change? I mean, it's the 1-bolt auto maintenance job. You drain it, unscrew a filter, put 1 bolt back in, screw another filter on, and refill it. Yawn. Whenever I finish building an engine, I always cut the first 3 oil filters open and inspect the insides of them to see what's flowing through my oil system. I do this after every build to make sure I'm not blowing a big fat hole in my wallet. You've seen me do this in other videos after major engine problems to diagnose the extent of the damage. If I did everything correctly and I find anything at all inside the filter, it's going to be inside this first oil filter. What I find will determine whether or not it even gets a second one. I'm looking for bronze or aluminum shavings which aren't magnetic. Bronze would be bearings and aluminum would be camshaft journals or oil pump housing. It's fairly uncommon to find magnetic particles like iron or steel in the filter because those materials are much harder than the bearing surfaces that all your moving steel parts are suspended by in the oil film layer. To break or wear down steel parts means the other parts are taking a real beating, and you're always going to see the bronze and the aluminum stuff first. If you break steel stuff, don't expect your engine to continue running at all. Steel parts tend to leave the block violently when they break. But so far so good. I don't see anything here that's suspect. The black gritty looking stuff that you saw in the filter is the actual end caps of the filter material that I broke apart. I found one red oil rag fuzzball, which likely made its way in from me handling it because it was still red. 2 flakes of aluminum and 1 flake of bronze total. Remember, this thing didn't get hot tanked. It got a mineral spirits bath with a siphon feed blowgun right here in my garage. It got brushed out, disassembled, and put back together. It's likely that all 3 flakes I found are remnants of the previous destruction. Now that the coolant system is empty, my attention is turning back to the radiator. No matter how bad I wanted this radiator to work out, it didn't. At least you know I tried to make it work. There are holistic remedies for this, ranging from adding a raw egg to the coolant, to black pepper, to store-bought remedies that plug up the leaks, but that stuff ends up being circulated and sticking throughout the whole engine block, head, and turbo. I'm not a believer in that kind of coolant additive. It might get you home, but it's not a permanent fix. I'm flipping pumped right now because my 24mm slotted socket that I made for the knock sensor perfectly fits over this fan switch. It's a little crusty, so I'm going to clean up the threads on my wire wheel and attempt to find a new O-ring seal for it. There you go. It looks like an O-ring from a 6AN fitting fits perfect, and I have a box of these things laying around. Still, what are we going to screw this thing back into? Oh hey, it just turned into an aluminum 2-row unit. No clue who makes this one, but the fan switch threads in just fine, and it looks like this is going to work. The radiator was actually on this car once before, and I bought it for the Colt. It's a squeeze to make this fit, and I'm going to make that squeeze far worse for myself by permanently attaching my radiator fans to it for airflow reasons, and also so that I can clean up the wiring on it a bit. But before I do that, my previous shroud was made to fit another radiator, and the position of the welds keeps it from fitting correctly. I cut out the sides of it so that I could sandwich them in between the fans and the radiator, and then use zip ties and backing plates to allow me to attach the fans through the radiator core itself. This is actually a similar means of attaching the fans employed by many aftermarket fan kits floating around, but this is a home remedy replacement that I'll accept. Backing plates for the zip ties aren't sitting on a shelf anywhere, so I'm improvising here. The hole in a washer is too big, and the washers with the correct size hole for a zip tie are too small. So I'm just cutting up and painting some chunks of sheet metal that I have laying around to make my own backing plates. I probably should have made these things a little bit bigger, but there's 6 of them and they're not super tight. The rubber hoses sandwiched between these parts protect the core from damage from the fans, while keeping it tightly secured. I'm happy with that. Next up is the wiring. There's the fan switch harness, and there's the factory fan connector. The wiring is about 1.5 feet too long for this radiator, and it's damaged from heat and stress. My goal is to connect the best parts using the same gauge wires and to neatly attach them onto the assembly to make all of it easier to work on later if I ever have to. I'm cutting everything but the black and green wires off the fan switch. I'm attaching this to the ground side of the radiator fan circuit, but really it doesn't matter. It just opens and closes the circuit to make power flow or not flow. Power wire from this flows into the number 1 fan's white wire and out the black wire. Then it flows into fan number 2's white wire and out of its black wire. I've got the number 1 power and the number 2 ground wires bed off to the left here. We need the bullet connector junction on the 2 straight ones in order to attach these fans together. I could have soldered these together, but I have this junction, it saves time, and I can rewire the fans later easily if I want to like this. Because the fan switch is on the ground side, I'm using the green wire on the fan switch as its power in, and the black wire for ground to the factory harness plug. There appears to be enough wire here to do that, so I'm going to keep this short and just attach a weather-resistant heat shrink female bullet connector to the thermal switch's power wire, so I can simply plug the number 2 fan ground wire to it. On the black ground wire for the fan switch, I'm stripping, soldering, and heat shrink tubing a 12-gauge extension wire to bridge the gap between the thermal switch and an easy-to-reach location where I can just plug it into the engine bay harness. Oh, you have to refill this thing once in a blue moon. Okay, maybe twice. But anyway, on the radiator side of the engine harness connector, I strip and solder on the ground wire from the fan switch to the connector's ground wire, and as always, use heat shrink tubing to insulate my work. On the other piece of 12-gauge wire that I cut off of the extension, I'm installing another female bullet connector so that the number 1 power wire can reach the engine harness connector. Plug that in and secure all the wires to the fan shroud with zip ties, and that pretty much tells me right there where I need to cut and make my last solder connection. One more final cleanup and it's time to install this thing. But this thing's so big now that you can't just drop it in. It won't clear the J-pipe on the turbo, so that thing has to come back off. It really needs to anyway, and you'll see why in a minute. The other thing that needs to go is this one heat shield bolt because it'll destroy my radiator if I don't. Fortunately for me, the radiator drops right into the lower support brackets and fits like a glove. Man, that looks great. Unfortunately for me, the upper brackets don't line up at all no matter what I do with them. And in addition to that, this upper radiator hose isn't going to work either. I've got the old one that was on this radiator, so maybe it'll fit better. It looks like I'm going to need to brace this thing in place and make a set of my own brackets in order to secure it. Here comes the tape and drill bits again. This car is practically made of scrap metal. If this were a nicer car, I'd have peeled the tape off first and then cut it out somewhere else to avoid scratching it. Scratches are the least of this Elantra's problems. There's one more thing I need to explain. The way I had my wastegate teed off the blow-off valve was wrong. So I used a piece of brake line and a flare kit to make a hose end fitting and fabricated this vacuum nipple for my J-pipe. Fixing this right now will make installing a boost controller or a boost control solenoid much easier later on, and I'll need that done for the sake of a future video. All of you non-imperialists should appreciate me using the millimeter scale to properly size the right SAE drill bit for this job. It's this one. The boost source for the wastegate needs to be in front of the throttle plate. It needs to see intake pressure, not intake manifold pressure, in order to correctly regulate your wastegate. Factory 1G cars have it tapped in this location, but my J-pipe has no provisions for this. I'm drilling the right size hole in my J-pipe and getting Chad to weld it in for me. Time to punch some holes and finish putting this car back together with Rojo del Choco's help. I'll be back in a flash. well, we tried. This is the 4th time I've tried to get this welded back together now. It's not Chad's fault. This aluminum pipe is just so thin that every time we heat it up, it cracks right outside where the welds are cooling. So I'll give this a B+. There are 0 leaks on the J-pipe, injector seals, intake manifold, map sensor, or the intercooler core itself. With the boost leaks taken care of, it's time to set base timing. For this, it doesn't matter whether I use a 30-30 in the shot, a hairdryer, an actual timing light, or this duck hunt gun. There's no way to fit it all in here at once to show you what this is supposed to look like. I can't see the pulley, much less the timing marks in this car without some serious acrobatics. After connecting the power and ground clamps, which really isn't easy when you move your battery to the trunk, attach the sensor clamp to the number 1 plug wire and set the timing gun at 0 degrees of advance. But before I start, I'm just going to make one more thing easier for myself. I'm going to loosen up these cam angle sensor bolts before I fire up the engine. I have a brand new seal on it. Mine's actually hard to rotate while the nuts are loose, so I'm not worried about it rotating while it idles up to temperature. To check your base timing, you have to ground your timing connector on the engine harness. But if you have ECM link, then you can just click on the miscellaneous tab in your live ECU settings and then tick the ground timing connector checkbox. Let's get this thing at warm closed loop idle and set the base timing. I'm not really interested in showing you the whole engine warm-up process. If your narrowband O2 sensor doesn't cycle within 90 seconds from startup, or you throw check engine light codes from other failed sensors, you'll never go into closed loop. Closed loop requires that your coolant temperature is above 190 degrees Fahrenheit. It requires that your intake air temperature is less than 123 degrees Fahrenheit, and that your barometric pressure is between 23 and 31.5 inches of mercury. Those are the rules, I didn't write them. Every car will be different, so it's on you to make that happen. If you're stuck in open loop, it's pretty easy to see why in the logs. But because I did the work in previous videos to achieve closed loop, I'm in it. It looks like we're ready to go. After monkeying around for a few minutes to get a clean shot of the timing marks, I finally found it, and I know which way I need to move it. Turning the cam angle sensor clockwise towards the front of the car advances timing, and turning it counterclockwise retards it. The goal is to set it to 5 degrees before top dead center on a first generation 4G63. Once you've got it lined up correctly, it's extremely important that you lock all of the nuts down that hold your cam angle sensor in position. Also feel free to mark its clock position against the cylinder head. Changing your timing affects your engine's airflow characteristics, so if you start tuning airflow and haven't correctly set or verified your base timing yet, then you're wasting your time. I've never successfully captured this shot before. I've always had shutter speed issues. There's the timing mark, lined up at 5 degrees if you look carefully. The strobe fires with the number 1 spark plug to reveal the precise moment in the crank's rotation when your ignition fires. Simple but clever. I nailed it, time to move on. So now that base timing is set, these numbers show that there's plenty of other stuff here that we need to fix. Changing some of these things will affect other things, so really I'm just going to cover some goals to shoot for. The idle speed control position, for instance. You have to set it with every light bulb and electrical accessory turned off, including the radiator fans. It's the idle speed control motor's job to open up and allow more air in as you load up the engine so that it can maintain a smooth idle. And this means that you should set the ISC position in the lower portion of its range with no load on the engine to give it more headroom. So with everything off at warm idle, adjust the base idle set screw on the throttle body to get it to hover around 30. Backing off the BIS screw opens up the valve letting more air in, thus closing down the ISC motor. And screwing it in causes the ISC motor to open up. The further it's opened, the bigger the number. If your fan's cut on while you're adjusting it like mine did, wait for them to stop and it'll settle back down. Then continue adjusting. Once you're finished, you can choose to cover the BIS screw hole in low temperature RTV to lock it into position if you want. Some people have had these screws vibrate loose. It also helps to keep boost leaks under control, but replace the O-ring prior to resorting to something like that. So that's what the BIS screw does. It doesn't raise and lower your idle. Its job is to regulate the ISC motor. The ECU is what controls the idle, so if you're having a problem, check for boost leaks and vacuum leaks first, and then check to make sure your ISC motor is working properly. I have a video for that already. Once you've done these things, you can start to play with your fuel. I use global and dead time, as well as idle cells on my speed density table to adjust and get this airflow per rev value down to 0.25 grams per rev, because that's what the swept volume of 2 cylinders worth of air weighs at sea level for my engine. For a 2.3 liter stroker, it's 0.27. For a 4G64, it's 0.28. Lots of tuners have different theories about being 20 thousandths overboard or having cams with a ton of overlap or some other kind of contraption bolted on that magically changes the swept volume enough to make it weigh any differently, but .25 average is what I shoot for on my street tune. Follow the advice of the smartest guy, don't listen to me. You want to achieve this value and have your combined fuel trims as close to zero as you can get them. If combined fuel trims is all out of whack, adjust your injector dead time to get it close to zero. Know that if you do, your airflow per rev is going to change. To bring that back under control, use the first couple of fuel sliders or the idle cells of the speed density table to correct for that until both values look good. Once they do, it doesn't mean you got it right. It just means that you've pulled into the neighborhood of it being right. You'll notice this once you get into wide open throttle tuning. If you're using a popular brand of injector with ECM Link, there are lots of global and dead time baseline values available on the ECM Link wiki pages that can save you all this guesswork. But my injectors are not popular, so for me, there's a lot more trial and error. Boy, is my throttle position sensor voltage wrong. It's supposed to be 0.63 volts. In another video, I showed you how to manually adjust the throttle position sensor into range, and it's tedious. But with ECM Link, you have an even easier option. That option is to offset the range and baseline voltages of the TPS sensor. You need to capture the full open and closed ranges of the throttle position sensor. So get your foot completely off the fun pedal and floor it a few times, then stop your log. You can do this with the engine running or not running. You just need to do this while you're capturing a log. Find and select the part of the log where you did that, and then right-click it. There's an option in the menu to have ECM Link adjust your throttle position for you, so you don't have to do so much trial and error. It doesn't always nail it the first time, but you can either repeat this step or manually adjust it if it doesn't. These values are in the RPM and throttle position sensor tab, and once they're set, you have to save them to the ECU for them to do anything. Check those changes by starting another log and repeating the same steps. Examine the minimum and maximum values to ensure you see 0.63 to 5 volts in the sweep, and once you do, you're done. These are just the basics. Fuel, timing, and airflow tuning will give you better results once you get these values correct. Those videos, if I'm bold enough to make them, will probably start flame war after flame war because there are so many different approaches to tuning. What you're witnessing right now, despite all of the advice I just gave about tuning, is a problem that plagued my tuning for the past 2 months, and I couldn't figure out for the life of me what was causing it. This is something that took video editing to see and figure out what was causing the real problem. Notice that these values are still changing even though they were nearly perfect earlier. Changing one thing changes another thing, sure, but every time I cut my car off and back on again, it seemed like everything changed again. Notice how combined fuel trims are all out of whack, and the airflow per rev values have changed. This isn't just the result of hot start enrichment, that's actually turned off right now. I enlisted Robert's help from the Turbo Talon channel because of how new V3 is to me, and I couldn't have gotten as far as I have this fast without his help. Not only did he notice problems faster than I could have noticed them because of his level of experience, he had the patience to stick with me as I learned how to use speed density airflow metering and to help me balance my speed density tables. After time and time again, each of these values changed. Perfecting the tune on any given night was meaningless. The next trip out, those values were all wrong again. Some of you might have noticed that during this tuning session I had the old radiator in this car. It's because I didn't film this in order of how you should do it. I ended up having to start completely over from scratch and do all of this again. I just did things the second time the same as I did the first time, so I used the original footage. On some of my outings, I was making 10 psi at what should have been wastegate pressure. The next day it was 9, then 6, then 2.5, and then 0 at wide open throttle. There was nothing wrong with my turbo. I sealed up my boost leaks and crushed the blowoff valve to keep it all inside the pipes. I boost leak tested this thing past 20 psi until I blew the boost leak tester off the turbo, and I watched the wastegate actuator start working at 12.5 pounds of air pressure during my boost leak tests. I found no shaft play and ensured through testing that everything did indeed work properly. It did. But eventually, I couldn't build boost even at wide open throttle. After the wastegate nipple was installed and I managed to open the wastegate at 0 psi, and then I heard compressor surge, I finally figured out why the engine wasn't getting to eat any of the boost I was making. It was never making it there. I called Chad and asked him to bring me my shop vac. I was ready to test my hypothesis the moment he arrived. I had pulled both sides of the intercooler couplings off, plugged in the shop vac, pulled out the vacuum cleaner bag, stuffed my shop vac into the hose for the hot side, and bam! Found the problem. It's even embarrassing to have had a witness, but this explains why my engine wasn't seeing any of the boost the turbo was making. I had a dirty secondary air filter accidentally installed. This is a cut up section of a t-shirt and I don't ever use these around my shop. You can see that I have a bar and plate core because there are perfect prints of all the airflow galleries filthed right into it. I never would have guessed this thing was in here when I installed it because the pipes were still clamped to it. None of my tests or inspections could have caught this.
This is a stupid problem to have. But it is a problem nonetheless.
This rag caused me to miss the only track day that hasn't been rained out since this car's been running. And now that the Hyundai is no longer on the rag, I get to restart my baseline airflow and fuel tuning from scratch all over again. Just imagine how something like this will change your airflow tables. Start over, Jafro. Well, I hope you enjoyed me owning my mistakes in this episode. All this stuff is sorted out and this is a better car than it's ever been. I hope this is a worthwhile example of the kinds of things you might have to do after reassembling your turbo project. Or at the very least, what was required of mine. Please feel free to like, favorite, or subscribe, or leave a comment in the guest registry below so that I know you were here. Until next time, stay tuned.